10,000 cubic kilometers of water burst from Lake Agassiz into Lake Superior near Thunder Bay and spilled into the Atlantic Ocean. Importantly, this flood coincided with the advent of the Younger-Dryas, a 1,000-year global cold snap which began about 12,900 years ago. That's the most important thing. They do suggest here at the end that they're open to this possibility. In his quest for answers, though, he's found a new avenue to explore. About the time the Younger-Dryas cooling period occurred, a comet seems to have collided with the Pleistocene ice sheet that dammed Lake Agassiz. And I would propose that one of those cometary impacts was right there. And it wasn't the draining of Lake Agassiz, it was the melting of this area right here by the impact that caused the huge floods that swept down into Lake Superior. So there's a close-up view, and you can really get a sense of the basin-like nature of the feature. Its raised rim in the southern quadrant, you can see, is highly dissected and channelized. All right. So, I guess we'll look first at this Lake Nipigon thing. All right. So one of the potential trips, Bradley and I were going to undertake this trip last fall, and we were going to go with George Howard. I don't know how many of you know George Howard. I know you guys know George, right? Yeah, George is an awesome guy. Yeah. He runs the Cosmic Tusk website. We've done some field trips with him. He's also a founding member of the Comet Research Team, which has now grown to over 60 scientists internationally. So we were setting this up, and we were planning to go, and he had reached out and contacted John Shaw. Now, you guys probably don't know who John Shaw is, or was. John Shaw was probably the world's foremost expert on drumlins, which are a very important diagnostic landform for tracing and tracking and documenting evidence for gigantic megafloods. And what he did was propose that drumlins were formed by huge floods shooting underneath the ice sheets, forming the glacial tilt into these fluvial, boat-like, aerodynamic forms that look like almost inverted spoons or inverted boat hulls. And he was going to join us there. He had responded to George Howard and said he would love to join us there, but then regrettably, like a month later, he passed away. So he was probably in his 80s or late 70s. But what he proposed was a very controversial idea when he first proposed it in the 80s, just as J. Harlan Bretz's ideas of gigantic megafloods that he proposed in the 1920s. Just whipped up a storm of controversy and attempts to suppress. And there was one criticism of Shaw's theory that I thought was legitimate, and that was, just like with Brett's, his critics said, okay, so you say there's this big flood. Well, where did it come from? And he didn't really have an answer. So then his critics said, well, if you can't tell us where it came from, then there was no big flood. They did the same thing with John Shaw. They said, if you can't tell us where these gigantic subglacial floods came from, then they didn't happen. Well, what he was proposing was some kind of a reservoir that would have to form in the ice or on the ice, the great ice complex that existed at the end of the last ice age. And all of his critics savaged that and said, no, it wouldn't work. You can't store a significant volume of water on the ice. Now, this is ironic because this is what I've been saying for decades now about the prevailing theory about the Missoula floods, is because they're saying that the conventional idea is that you had this massive lake, over 600 cubic miles of water, 2,100 feet deep, held in by glacial ice, right? Which could not be possible for a number of reasons we're not going to get into tonight because it just would take us too far afield. But they essentially said the same thing to John Shaw, and they were right about that. What they weren't right about, though, So they said, well, because there's no way to store, like one of John Shaw's subglacial floods required 80,000 cubic kilometers of water. That is just an astonishingly, that's like 20,000 cubic miles of water. That's like all the Great Lakes together multiplied by several times over, right? And they said there's no conceivable way you could ever accumulate that much water, right? And they were right. But see, now we have a different paradigm. This new paradigm is that no, you don't have to create a slowly accumulating reservoir of meltwater that suddenly busts loose and, you know, flows out and basically drowns half the landscape of North America. Because we now have a mechanism to induce instantaneous melting. Now, this gets us to the Younger-Dryas impact hypothesis, which I wish we'd had more time to talk about, because this is one of the most important scientific hypotheses out there in this day and age. And it's basically the idea that the Ice Age was ended by an impact or series of impacts, which is the model I lean towards. The collapse of the Clovis culture and the sudden mass extinction of all the great megafauna that lived in not only North America, but South America, Eurasia, right? So something really profound happened around 12,900 years ago. And something really profound happened again about 1,300 years later. And those two dates bracket what's called the Younger-Dryas. Now, what's interesting to me is like 5 years ago, nobody but a small group of very highly specialist glaciologists and paleoclimatologists and so on knew the term Younger-Dryas. Now millions of people know the term Younger-Dryas. I'm constantly seeing the Younger-Dryas coming up in conversations and things on the internet, people talking about it, which is very gratifying to me because I think I had a small part to play in helping getting this idea out there. The idea that our planet dramatically changed around 12 to 13,000 years ago. And the world we've inherited is a very different world from the world of our Stone Age, our Pleistocene ancestors. So one of the constant criticisms of the impact hypothesis from the critics is that, well, just like with the Cretaceous Tertiary boundary impact of 66 million years ago, that had to withstand a decade of withering attacks before it was finally accepted. The idea that there was a great impact on Earth 66 million years ago that destroyed the dinosaurs, right? Well, it's now been 12 years since the first scientific publication of the Younger-Dryas, regarding the Younger-Dryas impact. It's still not fully accepted. One of the reasons is that the KT boundary, when it was first proposed in 1980, didn't have a huge political facade to have to bust through. The Younger-Dryas is much more political. Because for one thing, obviously 66 million years ago, there were no humans. 12,000, 13,000 years ago, there were humans, right? And also this idea is entrenched that humans killed off the megafauna. And this idea has been around for half a century, and it's kind of ebbed and flowed. It was pretty much on the way to being fully dismissed until about a decade ago. And then it got revived because it provided evidence that we humans were capable of perpetrating a mass slaughter on a planetary scale. And it fits right in with certain political agendas that are now very prominent. And so when this idea got proposed that maybe it was something from space that killed the megafauna, it was soundly rejected initially and attacked. But one of the principal criticisms and objections, just like with the KT boundary event, was, well, you got to show us a crater. That's the smoking gun. Well, you know that not so long ago there was a crater found under the Greenland ice sheet. It was, what, 19 miles in diameter? About that, yeah. Dating those at this point too precise to say definitively that it was Younger-Dryas. It very well could be. Apparently it's still hot under there, which means it's young. But we still don't know. Is it a Younger-Dryas impact, or could it be of an impact 20,000 or 30,000? We don't know. But we're going to need to get more data. But so what I began to do was to begin to look at the pattern of melting. And what I soon realized was the melting was not what you would expect from a traditional concept of glacier recession. Now, we had about 400 years of the Little Ice Age. We came out of it, the planet came out of it in the mid-19th century, and during the Little Ice Age, the 400 or 500 years of the Little Ice Age, glaciers worldwide grew to the greatest extent, get this, the greatest extent that they have been in 10,000 years, since the end of the Great Ice Age. Well, modern glaciology was born with observations of the warming that came mid-19th century when these worldwide Little Ice Age glaciers began to recede. So one of the things that the scientists did was they said, okay, let's measure these recessional rates. Typically, you might get anywhere from a few feet up to 20, 30, 40 feet per year, right? We look at these recessional rates, and what we see is that the ice basically recedes from its margin. We didn't get to go see the moraines in the Animas River Valley. We did take the first group there, so you could see moraines. Moraines form when the ice comes down. We talked about this, I think. Creates a mounded, arc-shaped mound, and then it recedes, and it creates this very distinctive glacial landform as the ice recedes, right? Well, so now we have what you would consider a normal glacial recession. That's what we've observed. You have outwash as the glacier recedes, volumes of meltwater outwash and create a nice, almost level plain, sometimes speckled with boulders and rocks and things. But when we look at the melting of the last ice age, it didn't really do that. It did it somewhat, but what we see is there seems to be two kinds of melting. And the key, I think, was John Shaw's work on drumlins, because the drumlins, there are massive drumlin fields up under where the ice would have been. And if you follow those drumlins, they emanate from epicenters. And many of those epicenters are occupied by extremely deep lakes, right? And so among these, the one I'm going to focus on first is Lake Nipigon. And it says, evidence for extreme melting and catastrophic flooding. So the following collection of maps and images have been retrieved from Google Earth, various internet sites, and journals as part of pre-reconnaissance research conducted prior to field investigations, which is what we had hoped to do last fall. But things got too complicated. So here's a general map of the Great Lakes region, and Lake Nipigon can be seen right here. Just almost north of Thunder Bay. Now, any drive, say from Minneapolis or Duluth to get up there would require driving along the north shore of Lake Superior, which is spectacular because Lake Superior was a conduit for huge volumes of meltwater. Here was one part, here was another part, and you can see the scouring on the floor of Lake Superior. In fact, if you could drain Lake Superior, the floor of it would look like the Channel Scablands of Washington. See, this is a huge wash of mooring across here, and then the erosion continues down into Lake Michigan, and so you had a huge subglacial flow coming this way, and then emanating down here, carving out what is now the Illinois River before it reached the Mississippi and ultimately flowed to the Gulf. You had other flows, which we can look at later, but we're focusing on this right now, so let's go ahead. This is just a closer up so you can see some of the scouring that's on the bottom of these lakes. That scouring is indicative of highly pressurized subglacial meltwater, forcing its way under the ice sheet, and then scouring the bedrock in the process, sometimes hundreds, even 1,000 feet deep. Some of these channels here on the floor of Lake Superior are gouged out 1,000 feet deep. Extreme scabland erosion on the floor of Lake Superior. Okay, so here's Lake Nipigon. So surface area, 1,872 square miles, 60 miles from north to south, 40 miles east to west. Average depth's 180 feet. The maximum depth is 541 feet. And it's basically a bowl-shaped depression. And here we're just looking a little bit more of a oblique view. Lake Nipigon occupies a topographic bowl or basin with an upraised rim around it. The west rim of the bowl lies about 700 feet above the lake surface, and about 1,200 feet above the deepest part of the lake. The northern part of the rim lies roughly 400 feet above the lake and about 900 feet above the lake bottom. The rim has a shallow saddle or col at the northeast quadrant up here that lies only about 150 to 200 feet above the lake surface. Then coming around clockwise, the rim begins to ascend in elevation, again to the east of the lake, and rises to above 1,500 meters above sea level in the southeast quadrant, right here. So now it says, see the next slide. So here are just some elevations, and you'll notice 1,540, 1,540, right? Well, what this is showing us is that this was once continuous at the same elevation. And this particular area here, notice 746. So this is almost 750 feet lower. So there's a trough in here that's about 700 to 750 feet lower than the surrounding rim. I'm going to skip this slide for now. Okay, so here's James Teller, a well-known paleohydrologist, geologist. So this was published in the University of Manitoba Bulletin in 2008. So he's talking about how, between 13,000 and 8,000 years ago or thereabouts, the world's largest lake played an integral part in a catastrophe that changed the world. But what exactly was its role? Now, what he's doing is he's assuming that Lake Agassiz, which was this gigantic inland sea of fresh water, glacial meltwater, that drained in 3 different channels to the oceans, including up to the Arctic Ocean. It's a gigantic body of water. I mean, you literally wouldn't have seen across it. It would take you days to sail across it. It was like an inland sea. Okay. Part I want to call your attention to, so Teller researches past climate and hydrological changes using sedimentary records from lakes as a guide. His research primarily focuses on Lake Agassiz, its birth, death, and its outbursts in between. It's a formidable undertaking because of the complexity of the lake's history. But he goes, Teller was the first to publish that overflow from Lake Agassiz was periodically catastrophic. On our road trip with Graham Hancock, we took him to the outlet of Glacial Lake Agassiz, which is right down here on our way to the Twin Cities. And at that outlet, there's a lake and a town. The town is Big Stone, and the lake is Big Stone Lake. The reason is, obviously, because there's huge stones there. And huge stones, are, especially if they're rounded, as these are always an indication of a gigantic flood. Now here's what he goes on to say. There was a fire, and the fire season was serendipitously harsh that year, and we saw acres of giant boulders and deeply eroded bedrock that led me to conclude that there had been a gigantic flush of water across that area from Glacial Lake Agassiz into the Great Lakes. Then in 1989, at the urging of oceanographers from Columbia University, blah, 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 he co-authored a paper for the journal Nature describing for the first time how 10,000 cubic kilometers of water burst from Lake Agassiz into Lake Superior near Thunder Bay and spilled into the Atlantic Ocean. Importantly, this flood coincided with the advent of the Younger-Dryas, a 1,000-year global cold snap which began about 12,900 years ago. That's the most important thing. They do suggest here at the end that they're open to this possibility. In his quest for answers, though, he's found a new avenue to explore. About the time the Younger-Dryas cooling period occurred, a comet seems to have collided with the Pleistocene ice sheet that dammed Lake Agassiz. And I would propose that one of those cometary impacts was right there. And it wasn't the draining of Lake Agassiz, it was the melting of this area right here by the impact that caused the huge floods that swept down into Lake Superior. So there's a close-up view, and you can really get a sense of the basin-like nature of the feature. Its raised rim in the southern quadrant, you can see, is highly dissected and channelized. It's in some of these channels, in a way, are almost remindful of the canyons we saw in Mesa Verde. They're shear walled, they're deep.
How thick would the ice have been right there at that time?
I'm gonna guess probably somewhere between 2,000 and 4,000 feet. Maybe deeper, maybe deeper. I wouldn't say it was more than a mile though. And here's a colored digital elevation model of the lake where you can really begin to see this amazing plexus of erosional forms along the southern quadrant and the channels that water would have flowed out of. And here we see these islands are actually sediment that have splayed out from this erosion here.
So Randall, are you basically saying that a comet impact rapidly melted an ice sheet?
That's the hypothesis.
That is so cool.
And this is coming from somebody who has a degree in geology. The other spillway would have been here. This is water would have spilled over this way and flowed into Hudson Bay. So I'm showing here the suggested outflow paths. The southern outlet trough bears all the marks of an extremely powerful catastrophic flood. Now, interestingly, I had been doing all this research and putting this together before I found the article by about James Teller's work. So I had no dating on it. All I was going was for the geomorphology.
So is that why it's bowl-shaped then from the impact? Or?
Yes, well,
Really?
yeah, that would be one of the key indicators there. Yeah, I'm sorry this is not showing up that good, but let's look at some of these, the topography of some of these features here.
So is the idea to go to Lake Nipigon and find evidence of an impact that,
Yeah.
that proves it? So we went to Impact Crater recently
In Arizona.
in Arizona,
Yeah.
and they dug and searched and tried to prove for so long that it was an impact, but then they ended up finding out that everything that they thought should be there was vastly scattered.
Yeah.
So it just makes me think, you know, it might be a little more
And the problem here too is if you've got an impact in the ice sheet
Yeah.
with huge volumes of ice that then melt, and that melt water just floods over the region, it's going to obscure things quite a bit. But there's no question now at this point that there was catastrophic flooding. We have recessional cataracts here, they're all over the place. And we have these plucked cliffs that we talked about, and you learned about how the water flowing will pluck. So you've got, all of these are receding cliffs right here. There was a major flow that came down what is now the Black Sturgeon River, came down through here and left almost a coulee-like feature. Let's go to right here. And I actually remember being about 8 or 9 years old. We drove up with my dad, and somewhere along the way he found an overlook. And I've looked on the maps, I haven't been able to find it, but he found an overlook on this Black Sturgeon River spillway. And I can still remember getting vertigo when I stood on the edge and I looked into this massive chasm here. Because this is really a very big feature. You know how we've been talking about the concept of an underfit river? Here's another beautiful example of it. So you had many erosional forms all in here where the surrounding material was washed away by the floods. We have channels. I mean, pretty much everything that, we have streamlined forms in here that are shaped by the flowing water. All of these are indicative of giant floods. Let's go back to our slideshow. Okay, so this is near the southern end. So you have this, as it says, serenely beautiful today, scene of an extreme diluvial catastrophe circa 12,900. Here's an example of one of those erosional forms. It's tapered on the front, it's elongated. The axis of elongation is in the direction of current flow. And we can see features. Notice right here, you see that's kind of that like a terrace, a mesa-like feature, just like we were seeing in the distance from Chaco, from Chimney Rock and Mesa Verde. You can see it right here. So yeah, floods, we can see flood channels carved here. We can see another one coming down here, like this. So this is the same image. Digital relief map. Look, the scale got a little different, but that's okay. You can see here. See this? That's it. That's what's called a streamlined erosional residual. And again, that's one of the things you look for is these shaped hills. So they're showing pathways of floodwater. Now, what I would be interested in is finding sediment piles and searching through sediment piles for things that look like either direct pieces of an impactor or impact-produced proxies. This is the view over Ruby Lake, and this is a channel that's been cut. Bear in mind, when you have catastrophic floods, you get enormous scouring and erosion. Many of the lakes, especially the ones like you'll see out in the scablands in eastern Washington and western Montana, are scour trough lakes. They're the puddles that are left in these deep scours after the intense erosion is over with, see? And that's exactly what this Ruby Lake is. Notice the cliffs, okay, so that you can kind of get a sense of what it looks like in the field.
Is that Brad?
What? No, but see, obviously we need Brad, but he needs to be right up here on the edge.
Right.
With his toes curled over the edge.
That'll be Russ.
You know what we could do is attach some safety lines to you, Brad, and then we can Photoshop them out later.
All right.
But so we're looking down this flood trough now. So these cliffs are basically 400 feet high. So this, again, before the flood, the land stretched across here unbroken. That's columnar basalt. Ruby Lake escarpment is an erosional product of the passage of floodwaters. Ruby Lake occupies a scour trough, a very typical feature found throughout mega flood carved landscapes. Very similar exposures occur through the channel scabland of Washington state that were created by Missoula floods. That's a Ruby Lake overlook. And I was thinking what could be really cool is if we, do any of you do high diving? No?
Ready, does.
I would try it.
Talking about them wingsuits.
Sleeping
Yeah,
giant.
swimsuits.
This is an erosional form,
Oh, wow.
remnant that's known locally as the sleeping giant. And here we have a slot canyon. Notice, remember we did this, I was showing you how slot canyons form when you have a crack in the rock and it gets opened up by floods. And you end up with a deep canyon like this with straight walls. That's exactly what we have right here, a slot canyon. And there are numerous slot canyons that lead into Lake Superior. See, this is not slow, gradual erosion. This is something that happens in a geological instant. Slot canyons with sheer vertical walls created by the erosive passage of high-pressure floodwaters through pre-existing faults and fractures in the bedrock. And then we got a couple of canyons that show up here, and these are recessional cataract canyons. So what happens is the water is sweeping over. It first comes as a sheet over the ground, and then it gets channelized. And once it gets channelized, it starts down cutting, and then once it's down cutted deep enough, the water flowing on the surface will then be captured by those channels. And then what will happen is the water, as it's focused into these channels, will eat its way headward or eat its way up current by plucking. Just like Niagara Falls is now doing at a much slower rate, right? But this is happening over a matter of days or maybe a few weeks. So these are the kind of channels that I'm interested in exploring. And from the ground, they look like this.
Wow. Holy shit.
This is examples of canyons formed where subglacial sheet floods become channelized, a typical process in flooding when a flow which is spread out becomes focused and confined to a channel. The focused flow subsequently cuts down below the pre-existing surface, simultaneously widening and deepening a pre-existing zone of bedrock weakness such as a fracture or fault. And there's the mouth where it's opening out. So the floodwaters would have been coming out this way and then gushed out into this basin here, creating enormous amounts of sedimentary deposit as they did so. So these are the kinds of features that emanate from that southern quadrant of Lake Nipigon. And yeah, we can do some zip lining while we're there.
Oh yeah.
You're an expert at that, right, Ross?
I think so.
We can walk across this hanging bridge.
That's so fun.
Wow.
And then we've talked some about the vorticity of highly turbulent water and how it creates potholes in the bedrock. So on the last day of our trip with Graham, we took him up to St. Croix Falls along the St. Croix River, which was in the pathway of this flood water, right? And in a constriction between two layers of basalt bedrock, the water was forced through, and it created these huge potholes, some of them 20 feet wide and 80 feet deep, that were produced by this. And again, literally overnight. They're not being formed now. Now they're just gradually, of course the Park Service will go in and clean them out sometimes. If you left them alone, they just fill up with stuff, and eventually that stuff would lithify and you wouldn't even know they were there. But here is a pothole. As it says, it's a Devil's Crater is a testament to the incredible power and turbulence of the meltwater currents sweeping over the western rim of the Nipigon Basin. This is a gigantic pothole formed by colking in deep, swiftly moving floodwaters, in this case probably subglacial. And then there's a trough, an erosional trough emanating out from that. In fact, this may have even been a secondary, smaller impact that hit right here. And then, once it gouges out the ice and possibly some of the bedrock, you're going to have a huge amount of inrushing water into that cavity, which is going to be highly turbulent, and then be able to, especially because if there's an impact, it's going to fracture the bedrock and make it easy to pull it out of there. And that's what we see right here. So I'm thinking this might be evidence of a smaller tandem impact. But here you can get a sense of the size of the thing by the canoe in there. The lake is about 220 feet deep. The crater walls are about 220 feet in height, making the full depth of the pothole about 440 feet. With a width of about 660 feet, this has to be one of the supreme examples of vorticular cavitation on Earth. Note canoeists for scale. You up for that, Gage?
100%.
100%. All right, man. Cool. So here, I don't know why it's so bright, but yeah, here you see the Black Sturgeon spillway. Water flow is from upper left to lower right. Toggle to the next slide to see additional flow paths. And here is a oblique Google Earth view of the spillway. And you can see the modern river in it is minuscule compared to the size of the channel. Another example of your, what is it, Graham?
I can't remember.
A what?
I can't remember.
Scale variance.
Underfit.
Underfit river.
Yeah.
Underfit river. So here's that one, and then this is comparing, check this out, Brandon, Moses Coulee. So here's a side-by-side comparison at the same scale of the Black Sturgeon Spillway and Moses Coulee. Moses Coulee, as it says here, Moses Coulee ranks as one of the most magnificent ancient megaflood spillways on Earth, carrying at its greatest discharge over 300 million cubic feet per second of raging torrential floodwater. Black Sturgeon Spillway is about half the capacity of Moses Coulee, but is still a very impressive example of a relic channel cut by gigantic water flows that far exceed anything on Earth today. So somewhere in here, when I was about 8 years old, I was standing with my dad looking into this thing and getting vertigo. Only many years later did because I always remembered that. And only many years later did I put it together. You know, oh, right. So there's my proposed ground zero for cosmic impact. Now, of course, this is, at this point, purely hypothetical. But if you take this away, then the explanation for the catastrophic flooding, the existence of the deep basin, and all these other features, there's no explanation for it, really.
Right.
So that is a trip that I would very much like to do. And there's amazing country around there. There are lodges for rent. And really, I'm thinking even 4 days would be enough. Maybe take a day to arrive, 4 days to explore, collect samples, maybe 5 days.
10.
So that's one idea.
Randall, usually what you look for in impact sites is shocked quartz.
Shock quartz.
It's a large part of it. Do you think the ice sheet was too thick to do any sort of that action? Like, is the data just melted?
That's the problem.
That's
See, we're looking at a whole new definition for impact cratering when we start talking about the effects of impacts into ice sheets. And we should not expect to find something like the classic crater in Arizona. Because if that crater in Arizona, when that struck, there was 3,000 feet of ice over it, it wouldn't have looked like it looks now.
Yeah.
It's hard to imagine it would even make it to the earth through 3,000 feet of ice.
It does.
So that's just about the Nipigon proposed trip.